Okay, let's get started. Hello, everyone. My name is Sahong, and today I'm going to present our paper titled Horizon Reduction Makes RL Scalable. So in this paper, we try to answer the following question. With an infinite amount of data, compute, and model capacity, will current Q-learning methods solve any tasks? So basically, we're asking whether Q-learning is truly scalable, such that all we need is just to provide more data and compute, or it is not, so we need additional algorithmic advancements to scale up Q-learning. So that's the question that we try to answer in this paper. And what we did is to actually simulate this question as follows. So basically, we prepared several previously unsolved complex robotic tasks. Like for example here, this is cube manipulation task where the agent has to perform 8 consecutive pick and place manipulation in a row. And there's another like combinatorial puzzle task where the goal is to somehow press some appropriate set of buttons to match a target board configuration, like turning everything in blue. And maybe the other one is humanoid control, where the agent has to control this high-def humanoid agent to navigate through the maze. And these are really complicated long horizon tasks, up to 4,000 environment steps. And on these tasks, we collected almost near infinite data, so that overfitting is virtually impossible. And specifically, we collected up to 1 billion transitions with 10 million atomic motions. And this is actually even larger than, potentially larger than one of the largest robotic data sets to date, including OXE. And here, the data set consists of trajectories that look like, this, where each trajectory somehow performs random atomic motions. Like for example, in this manipulation task, the dataset trajectories randomly pick some object and put it at some other place or on top of other random blocks. And we collected a lot of such data, like up to 1 billion transitions. And we train a goal condition RL agent. And at test time, we ask the agent to solve some goal-reaching tasks. Like for example, here, the task is to stack 4 blocks at this specific position, like that. That's basically our experimental setup. And importantly, to solely focus on RL scaling, we try to remove all confounding factors. For example, we try to focus on offline RL to abstract away exploration. And also, we idealize the experimental setup as much as possible, for example, by ensuring sufficient state coverage and data, and use state-based observations or use in-distribution tasks so that we don't get confounded by anything other than the fundamental scalability of RL. In particular, such as like exploration challenges or distributional shift. So we don't want to be confounded by those kind of things, and we only want to see whether Q-learning scales with data and compute or not. So that's basically the important point here. So as a warm-up, here are some scaling curves on easier tasks. So for example, here we have 2 cubes, cube double. And on top of this task, we train behavior cloning, BC, and offline RL with increasingly large data sets from 100K to 100 million transitions. And they work pretty well, right? So here, the x-axis is the size of the data set. And you can see that as the data grows, the agent can eventually achieve 100% success rate with enough data, both with BC and offline RL, including IQL, CRL, and SAC plus BC. These are some representative offline RL algorithms. And on slightly harder tasks like puzzle 4x4, well, BC is not able to solve the task with lots of data because the data set is pretty much unstructured. But still, if we train offline RL, like IQL or SAC plus BC with enough data, then they can eventually achieve 100% success rate, being able to scale. So that's good. The problem is that when the task difficulty becomes higher, when the horizon length becomes longer, things get changed. So here, this is puzzle 4x5, which is much harder than the other two environments. And we trained BC and offline RL agents with 1 million to 1 billion data sets. And first of all, BC completely failed. Regardless of the dataset size, it was not able to achieve any non-trivial performance. The problem is that even RL completely failed to scale. That is, even with more data, their performances plateau without improving performance. And on harder tasks like cuboc tuple, it's even worse. So regardless of the dataset size, none of the algorithms were able to achieve non-trivial performance on this the hardest task in the benchmark. So what's wrong? Well, okay, maybe you may ask, maybe we should have used better models, larger models, or maybe better pulse architectures and so on, or maybe better hyperparameters. So we somehow try to apply these kinds of quick fixes to see whether we can solve this scalability issue by tuning hyperparameters or making model larger and so on. For example, we tried larger networks, better pulses, larger Q ensembles, smaller learning rates, and so on. But the result was that none of them worked across the board, and they're not able to solve the fundamental scalability of issues of BC and offline RL. And in the paper, we have this large observation table showing that these quick fixes are not very effective to solve this issue. So as an alternative hypothesis, maybe potentially still a better hyperparameter could have improved performance, but maybe as an alternative possibility, Q-learning is not yet scalable in its current form, at least to complex long horizon tasks. So I think this is yet another possibility that we can think about. Okay, so if this hypothesis is true, then what's the problem? Well, in this paper, we claim that the problem is actually in the objective of Q-learning. In particular, if you look at the objective of Q-learning or TD learning, we know that the target is biased. That means that R plus gamma Q bar is not equal to Q star. And this is bad because this is not only biased, but the biases accumulate over the horizon. So this is the compounding error problem in Q-learning. And we claim that this bias accumulation or error accumulation is the main culprit that prevents RL or Q-learning from being scaled. And that's very hard to mitigate just by scaling up data and compute. So that's the main claim. And in the paper, we experimentally showed that this is somehow the case through some controlled analysis study, where, as you can see in this figure, as the distance to n gets larger, the bias accumulates more and more, and this is very hard to mitigate just by scaling up data or model size or compute. Okay, so if this hypothesis is true, then how can we fix Q-learning? We claim that in order to scale RL, we must reduce the horizon length, or the effective horizon length, or the number of biased TD backups. The simplest way to do this is to use n-step returns. For example, this is the objective for n-step TD learning, where we don't get backup from sh plus 1, we get backup from sh plus n with rh to h plus n minus 1 being the discounted sum of rewards. And we evaluated this n-step TD learning with the same amount of data from 1 million to 1 billion on, for example, puzzle 4x5, where previously SAC plus BC failed to scale. And then if we test n-step TD learning, n-step SAC plus BC, we found that this is actually the first technique that enabled scaling of RL, as you can see in the second figure. So what really this tells us is that n-step TD learning is not just a small trick to make training faster or more efficient. It actually improved the fundamental scalability of RL by reducing the effective value horizon, by reducing the number of biased TD backups. So that's one of the main takeaways from this this work. But this is not the end of the story. So is n-step TD all we need? So on this even harder task, like cuboid tuple, if we train SAC plus BC, as I showed earlier, it completely fails. But unfortunately, n-step SAC plus BC didn't help either, even with value horizon reduction. So in the paper, we hypothesized that in order to truly scale up Q-learning, we also need to reduce the policy horizon. And here, the policy horizon reduction means we need to use hierarchical policies so that the effective horizon length of each level can be reduced. So in the paper, as an algorithm that performs both value and policy horizon reductions, we propose a new approach. It's a very simple full hierarchical RL method called SHARSA. And here are the main objectives. I think for the length of the talk, I'm not able to maybe go through all the details, but in a high level, the value learning objective is n-step SARSA. So it's basically n-step returns to perform value horizon reduction. And we train two-level pulses, a high-level policy and a low-level policy, and both of them are trained with flow behavior cloning. And then we also apply rejection sampling to the high-level policy to enable RL in some sense. So this is really simple method, but that performs both policy and value horizon reductions by using n-step returns and hierarchical pulses. And that's what we call SHARSA. And we show that if we evaluate SHARSA on this task, cuboid tuple, previously both SAC plus BC and n-step SAC plus BC failed to scale or even failed to achieve any non-trivial performance. But SHARSA is actually one of the first methods that is actually able to solve, actually able to achieve non-trivial performance on this very hard, very difficult task. And we found that this is the case just across the board, including cube manipulation, combinatorial puzzles, and humanoid control. So takeaways, A, Q-learning, and in particular one-step TD, may not be readily scalable in its current form to long horizon complex tasks. And the reason is that the main reason is related to bias accumulation or error accumulation. And horizon reduction makes RL scalable. So that's basically the end of the talk. And I also wrote a blog post called Q-learning is not yet scalable. So if you're interested, you can maybe also read the blog post or the paper. So that's all for me, and thanks for listening.